We've now found ourselves in a familiar situation. We know what integrals mean conceptually, but we're severely limited in how we can actually calculate them. Once again, is there a better way? The answer will reveal a deep connection between integrals and derivatives. By now, perhaps you've started to notice a trend in how we develop things in this course. And I want to take a second to make that trend explicit, because I've tried to make this an accurate representation of how mathematics is often developed in general. We often start with an idea of something we want to describe in the real world. We then figure out what sorts of calculations would let us express that idea, and analyze their consequences, often using specific examples. As we build understanding, we often end up coming up with a picture that gives us intuition about our idea. And after enough time playing around, we end up discovering the underlying relationships, which we can ultimately represent with algebraic tools, formulas, equations, rules, that sort of thing. Now, something that's often annoyed me about many math textbooks, especially calculus textbooks, is that they often do this in the opposite order. Usually the algebraic rules and formulas and sanitized definitions come first, sometimes with diagrams to try to help explain what's going on. Then you get a bunch of worked examples of how to do some practice problems, and finally, at the very end, if you're lucky, you might get a small handful of canned applications, word problems they usually call them, but only as an afterthought, if there's time. I think that gives the wrong idea of how mathematics is done and what it's all about. It took humans many years to come up with calculus, and that process took a lot of wrestling with ideas. My goal with these videos is to guide you to wrestle with those same ideas, so that the conclusions feel more natural and more satisfying. Think back to when we first talked about derivatives. We knew what we wanted them to mean early on, the sensitivity of a function to little changes in its input, or perhaps the rate at which that function changes at some given moment. And we figured out how to visualize derivatives, the slope at a single point on the curve, or more technically, the slope of the tangent line at that point. But the only way to calculate derivatives at first was to look at ratios between tiny changes, let those changes get smaller and smaller and smaller, and then see if those ratios converge on some destination. Pretty soon though, we managed to find algebraic patterns that let us efficiently calculate derivatives. All of those basic derivative rules for polynomials, trig functions, and so on, and then different ways of combining functions. With all of those under our belt, we were able to confidently add derivatives to our toolbox and use them to solve a number of interesting real-world problems along the way. Now, we're at the same point with integrals. We have their meaning, the accumulation of tiny changes into a collective whole. And we have a picture, the signed area between a function curve and the axis it's defined over. But, just like before, the only way we know how to calculate all but the most basic areas is to split our shape into thin little rectangles, the function value times a tiny interval. Add all those rectangle areas up smoothly, and then hoping that those areas converge on some value as we make that width smaller and smaller. What we'd like is to come up with a general principle that will unlock integrals in the same algebraic way that we unlock derivatives early. Well, I've got good news. There is a way. But I've got better news. In figuring out how to calculate integrals, we're going to find a profound and fundamental relationship between derivatives and integrals. How can that be? What does slope have to do with area? Aren't those two completely different concepts? I mean, you learned about them in two different classes. Well, as we'll soon see, it turns out that derivatives and integrals are actually two sides of the same coin. Pop quiz. What's the formula for the area of a circle? You likely learned this formula pretty early on. Pi times the radius squared. But why does that formula work? Where does it come from? There's a good chance that that wasn't included when you learned this formula. So let's take a look through the lens of integration. We need to chop our circle up into tiny bits so that we can add them together. There are a number of ways we could do this, but one particularly useful way might be to imagine it like a slice through the middle of an onion, with thin ring-shaped layers. If we chop through the rings at the top here, and then let them flop onto the table, then each ring would look pretty close to a rectangle. Now, if you do this with a real-life onion slice, you'll have a hard time, but imagine the rings are really rubbery, and that the slices are really thin. Let's find the area of one of those thin rectangles. The height would be the tiny increment in radius, and the width would be the circumference of that ring. And remember that the circumference of a circle is pi times its diameter, that is pi times twice its radius. So the area of each ring is roughly pi times 2r times delta r, the change in r. That r ranges from 0 for the inside ring to the whole radius of that circle. Now, if we add up all of those small areas of the rectangles, we should get a decent approximation of the area of the whole circle. And if we make those rings thinner and thinner, we should get a better and better approximation of the true area of the circle. So if we imagine those rectangles are infinitely thin, then the shape we'd end up getting is a triangle, whose base is the original circumference, pi times 2r, and whose height is the original radius, r. The area of a triangle is half the base times the height, so if we multiply all that out, we do in fact get pi times the radius of the circle squared. There's our familiar area formula. Represented as an integral, we found that the integral from 0 to r of pi times 2r dr is pi times r squared. Wait, hold on a moment. Look very closely. Do you notice something hiding there? No, not the pi, though both of those integrals do have a factor of pi in them, so let's use the constant multiple rule and pull them out. Then we'll divide both sides by pi. Okay, there we go. It seems like when we took an integral of 2r dr, we ended up with r squared. Where have we seen a relationship between 2r and r squared in this class so far? Well, the derivative of r squared is 2r, and we just found that the integral of 2r is r squared. That seems to be suggesting something that you may have suspected by now, that the integral is the opposite of the derivative. Could that really be? Let's see if that really works. Say we have a function f, maybe that looks something like this. We'll look at the area between 2 points, where we'll keep one point c fixed and let the other one x vary. Now, what happens if we nudge x by a tiny bit dx? Well, then we'll nudge the area by a tiny bit dA. That tiny bit can be approximated by a rectangle, whose height is f of x and whose base is dx. So dA equals f of x times dx. But then if we divide both sides by dx, we get dA over dx equals f of x. Since a was an area, an integral, that means the derivative of the integral is the original function. In some sense, slope and area are inverses of each other. That relationship between two seemingly disparate concepts is so important and useful that it gets a special name: the Fundamental Theorem of Calculus, or FTC for short. Well, at least that's the idea of the Fundamental Theorem of Calculus. The actual theorem itself has two parts that together will finally unlock how to calculate integrals. The first part of the fundamental theorem summarizes what we just did a moment ago. If we start with the function f and create the area function where one endpoint is fixed, then the derivative of that area function is our original function. What we'll often say is that the area function is an antiderivative of the original function. By the way, if the change of variables from t to x seems kind of weird, that's because we can't use x as both the variable we're integrating and one of the limits of integration. But anyway, the big takeaway here is the important thing, that area leads to antiderivatives. Okay, for the second part, suppose we want to find an integral from a to b of some function f. We could start by defining an area function, which we'll often write as big F, that integrates from some other fixed point c to a variable x once again. Then big F of a is the integral from c to a, and big F of b is the integral from c to b. Take a moment and pause this if you need to. Make sure you see what all the parts mean here. It's really easy to just get lost in all the notation. So convince yourself that all these fancy functions and integral signs really are talking about area. Now, how can we tie the area we want, the area from a to b, the integral from a to b, into the two integrals we do know? Can you see what we need to use here? Think back to your integral properties. We need the additive interval property. Based on how we drew it, the integral from c to a plus the integral from a to b is the whole integral from c to b. Now, let's do a little bit of algebra. If we subtract that first integral from both sides, then the integral we want from a to b is the larger integral from c to b minus the smaller integral from c to a. But that area function was actually big F. So that right side can be written more simply as big F of b minus big F of a. And the first part of the fundamental theorem tells us exactly how to find big F. Look for an antiderivative. So now we finally have a process for calculating integrals. Take your function f, find an antiderivative, big F, plug in the endpoints a and b, and finally subtract the right value at big F of b minus the left value big F of a. That right there is part 2 of the fundamental theorem of calculus. Okay, let's see it in action. Remember the bathtub problem from a couple of lessons ago? Let's see what the FTC tells us about how to do it. In 10 minutes, we ramped up from 0 gallons per minute to 6 gallons per minute. So the slope of that linear rate at which our water pours out is rise over run, 6 over 10, 6/10. So that rate function is r of t equals 0.6 times t. Then the total amount of water is the integral from 0 minutes to 10 minutes of 0.6 t times our width dt. So the fundamental theorem tells us that to calculate this integral, first we need an antiderivative of 0.6 t. So how would we find that? 0.6 t, t to the first power. Well, to take the derivative of a power function, we use the power rule. Bring the exponent down and then subtract 1 from the exponent afterward. So if we want to find an antiderivative, we'd have to reverse engineer the process. Add 1 to the exponent, so 0.6 t squared, and then divide by that new exponent, so dividing by 2. So that gives us 0.3 t squared. Is that really an antiderivative of 0.6 t? Well, you can check using the power rule. If we take the derivative of 0.3 t squared, then by the power rule, we do in fact get 0.6 t. So yeah, that is an antiderivative. Okay, so we've got an antiderivative. let's plug in our endpoints now. We often use a vertical bar as shorthand for plug these numbers into the function and then subtract the right value minus the left value. So we have 0.3 times 10 squared minus 0.3 times 0 squared. Lo and behold, if you work that out, you do get 30 gallons. That's exactly the value we found in the previous lesson. But rather than repeatedly recalculating areas with more and more and more rectangles, all we had to do was find an antiderivative, plug in the endpoints, and subtract right value minus left value. That's way simpler. Okay, you may have noticed something about how I've been phrasing things in this lesson. We've often talked about finding the derivative of a function, but here I've been saying we need to find an antiderivative. What's going on here? Well, it turns out that functions generally have multiple antiderivatives. For example, suppose we're wondering what function has a derivative of 2x. Well, x squared is one such function, but so is x squared plus 1. If we take the derivative of x squared plus 1, the derivative of 1 is just 0, so we just get 2x. Likewise, x squared plus any constant is going to be an antiderivative of 2x. So the most general possible antiderivative of 2x would be x squared plus c, where c can be any constant we want. If we take the derivative, the c will go away, and we'll just get 2x. This process of finding the most general possible antiderivative is so important that it gets its own name and notation. We call it the indefinite integral, and we write it the same as with a definite integral, but without those limits of integration. If you see an integral, but there's no limits of integration, then we're actually looking for the most general possible antiderivative, which then we could use when calculating a definite integral. So, when you're doing an indefinite integral, don't forget the plus c. Okay, for example, say we want to find the indefinite integral of x to the n dx, a power function. By reversing the process of the power rule like we did earlier, we can increase the exponent by 1 and then divide by the new exponent. So the indefinite integral is x to the n plus 1 divided by n plus 1. Plus an arbitrary constant c. Like I said, don't forget the plus c. That's often a very useful pattern for antiderivatives, so we'll give it its own name, the anti-power rule. Hold on a second. Earlier we developed a whole bunch of rules for derivatives. Are we going to have to do that again and get a whole bunch of new rules for antiderivatives? Thankfully, no. You already know most of them. All we usually need to do is take any one of our rules for derivatives and just think about it backwards. We'll occasionally simplify things a bit, like we did with the anti-power rule, and we might have to watch out for some constant factors and negative signs, but for the most part, you already know everything you need to calculate antiderivatives. Now, I do want to point out one last small but important thing with regards to terminology. Some people use the word integral and antiderivative interchangeably. Even I sometimes slip up and do this myself. And it's true that they're very closely linked, but they're not the same thing. The term integral generally has to do with signed area or accumulation, while the term antiderivative refers to undoing the derivative. Not much of a surprise there. The fact that these are essentially the same is the fundamental theorem of calculus, the notion that you can calculate areas by doing derivatives backwards. That's why the fundamental theorem deserves its name. It establishes a deep connection between the two big concepts of calculus, slopes and areas, derivatives and integrals. We'll be using the FTC plenty to compute integrals. And in fact, we'll dive deeper into the FTC at the very end of the course, when we work up to actually proving it. But for now, just take some time to process what it actually says, get some practice in with using it, and marvel at its beauty and its power.